Hi, in this video, we are going to continue our JEE Advanced series for conic sections. So we have done 4 videos on parabola so far. This is the next one. Here, first we'll start off with some examples, which will cover some of the topics that we discussed in the last class, and then we'll go to some more theory and properties. So we start off with the first question. This says, prove that the locus of the point of intersection of two perpendicular normals to y square is equal to 4ax is the parabola y square is equal to a times x minus 3a. So remember, we had discussed earlier that if two tangents were perpendicular, then their locus of the point of intersection is actually the directrix, right? We saw that earlier, that from any point on the directrix, we can draw two perpendicular tangents to a parabola. Now we are doing the other question where we want to find the locus of point of intersection of two perpendicular normals. So let's think about it. So we will say, let P x1 comma y1 be the point of intersection of normals to y square is equal to 4ax at points A, which is given by the parametric form T1, and B, which is given by parametric form T2, right? So basically we have to draw normals at T1 and T2, and those will intersect at the point P, right? So equation at normal is given by Tx plus y is equal to 2at plus at cube. We know that this normal has to pass through x1 comma y1 because x1 y1 is the point of intersection. And obviously here instead of t we can put t1 also and we can put t2 also. If I put x1 y1 here, you'll get tx1 plus y1 is equal to 2at plus at cube. And this is going to become a cubic equation, at cube plus 2a minus x1 t minus y1 is equal to 0. This is a cubic equation and it will have roots t1, t2 and t3. So actually there are two normals, t1 and t2 from here, and there is actually a third normal also that we are not talking about in this problem. So two normals are given. So using this cubic equation, we can write using Vieta's relation. If T1, T2, T3 are the roots of this cubic, we have first T1, T2, T3. The product of the roots is minus plus minus. So it is y1 by a. And therefore, we know the products of the normals is products of the T1, T2, T3 parameters is y1 by a. Now think about the equation of the normal. We know that slope of normal at t is minus t. So the slopes of the normals here are minus t1 and minus t2, right? So basically, we know that these normals are perpendicular. Therefore, we know that the product of these slopes will be -1, right? The question said that the normals are perpendicular. So the product of this and this is -1. So that means T1, T2 is -1. And if T1, T2 is -1, we can put that here. And therefore, we get T3 to be equal to minus y1 by a. So we are getting this result, T3 is equal to minus y1 by a, right? Now, obviously, the normal at T3 also passes through this point, right? So we can say, since there are three normals actually from this point, The normal at the point T3 will also pass through x1, y1. So if I write the normal at T3 equation, it will be T3 x plus y is equal to 2a T3 plus a T3 cube, and it passes through x1, y1. So I can write T3 x1 plus y1 is equal to 2a T3 plus a T3 cube. And we already know now that T3 is equal to minus y1 by a. So putting T3 here, we will be able to eliminate T3 from this equation, right? Notice that we have already eliminated T1 and T2 by coming up to the value of T3 as minus y1 by a. So now if I put this T3 here, we get minus x1 y1 by a plus y1 is equal to 2a into minus y1 by a and plus a into minus y1 cube by a cube. What we will get is minus x1 y1 by a plus y1 is equal to minus 2y1 plus, this is also negative actually, minus y1 cube by a square. Okay, so simplifying this a little bit, we will get multiply by a square throughout. So we get a minus a x1 y1 is equal to, this is minus 3, so minus 3 a square y1 minus y1 cube, right? So what we get is y1 cube is equal to a x1 y1 minus 3 a square y1, and we are getting y1 cube is equal to a y1 common x1 minus 3a, and one y1 gets cancelled here. You get y1 square is equal to a into x1 minus 3a. And this is the relation that connects the vertices of, or the coordinates of x1, y1 in an equation, right? And we wanted the locus of this point P x1, y1. So our required locus is replacing y1 and x1 with y and x. You get y square is equal to a x minus 3a. That's the required locus. So think about what we have done here. I will just go back to the previous screen. What we have done here is the locus of point of intersection of two perpendicular normals. So we said that let this be the point from where two perpendicular normals at these are being drawn, right? Or this will be the point of intersection of normals where normals are T1 and T2 are being drawn. So the normal equation is satisfied by T1 and T2. We got a cubic from there, and cubic has three possible roots. Any cubic will have either one root or three roots. It cannot have just two roots. So therefore we are able to conclude, since they have said that there are two normals, there are guaranteed two roots, which means there are actually three roots. And since there are three roots now, we have this relation by Vieta's relation, T1, T2, T3 is y1 by a. And because the normals were perpendicular, T1, T2 was equal to minus 1. So from here we got T3 is minus y1 by a. And then we realized that the normal through T3 will also pass through x1, y1. We wrote the equation of the normal. We put the point x1, y1 into it. And then used the condition T3 is equal to minus y1 by a to basically eliminate T3. That gives us a relation between just x1, y1, which is the locus that we needed. So that concludes this problem. Let's look at the second question. Two parabola have the same vertex and equal length of latus rectum, such that their axes are at right angles to each other. Okay. Now we have to prove that the common tangent, their common tangent touches each other, touches each other at the end of a latus rectum. Okay. So we have two parabola with the same vertex and they have equal length of latus rectum. So we can take one of them as y square is equal to 4ax. Their axes are at right angles. So obviously the other one can be x square is equal to 4ay, right? These are two parabola with uh, e same vertex and equal length of latus rectum. The diagram looks like this. One of them is like this and one of them is like this, right? Obviously, the common tangent will be somewhere like this, right? This will be the common tangent. We have to find the common tangent, right? So let's write the equation of the tangent to the parabola x square is equal to 4ay at point. Parametric point on this parabola will be 280 comma 80 square because it is in the different form. And the equation of tangent to this parabola at this point would be x1 is equal to 2a y plus y1. I'm not using the standard form of tangent equation, parametric form, because I don't remember that form. However, I know how to do this. This is not a standard parabola, so I cannot say tx plus y is equal to, or ty is equal to x plus 80 square, right? So I'm going to do this form, the point form, and here I will put 280 and 80 square. So I'll get x into 280 is equal to 2a y plus 80 square. 2a gets cancelled, and I'm getting the equation tx is equal to y plus 80 square. This is the equation of the tangent to this parabola at this point, right? Now, this equation is supposed to be also tangent to this, right? Okay. So let's think about how we will do that. So we have tx is equal to y plus 80 square is tangent to y square is equal to 4ax. All we have to do is find the point of tangency, right? Because we have to prove that the point of tangency is at the end of a latus rectum. So how do we check whether a line is tangent to a parabola? What we can do is simply solve the line and the curve equation and say that the discriminant should be equal to 0. So I'll say y square is equal to 4a, and instead of x, I can write y by t plus at, because from here I'm getting x is equal to y by t plus at. So I'm getting y square is equal to 4a by ty plus 4a square t. So y square minus 4a by ty minus 4a square t is equal to 0. This is my equation, and the discriminant here should be equal to 0. So what I will do is write that condition because it's supposed to be tangent. So discriminant is 16a square by t square minus minus. So plus 16a square t is equal to 0. So I'm getting 16a square common, 1 by t square plus t is equal to 0, which means 1 plus t cube by t square is equal to 0, which means t is equal to minus 1. So the point at which we have the common tangent to the original parabola, or equation of this common tangent will come now, right? Equation of this common tangent is coming. It is minus x is equal to y plus a. And at t is equal to minus 1, what is the root going to be? The root of this quadratic, if the discriminant is 0, is y is equal to minus b by 2a. So minus of 4a, so 4a by t by 2a, 2 into 1. So it is going to be y is equal to 2a by t. So y is equal to minus 2a. This is the point on the second parabola at which it is tangent. Y is equal to minus 2a. So obviously then x must be equal to a. because y is minus 2a, then it is 4a square, so x is a. So a comma minus 2a on the second parabola is the point where the line is tangent to it. And obviously you can see that this is the end point of a lattice rectum, right? On the first parabola, it would have been the point 280 comma 80 square, which would be minus 2a comma a. Again, that is also the end point of a lattice rectum for the first parabola. So here in this problem, we are seeing how to check whether a line is tangent to another curve. And this method always works, so you should know this method. Super important for you to be able to do it yourself. Let's move on to the third problem. The sum of ordinates of 2 points on y square is equal to 4ax is equal to the sum of the ordinates of two other points on the same curve. Show that the chord joining, show that the chord joining the first two points is parallel to the chord joining the second 2 points. This is a very easy question if you remember the theory that we have already discussed. So let the first 2 points be A, T1 and B, T2. And let the second 2 points be C, T3 and D, T4, right? So the sum of the ordinates of 2 points on this parabola. So the first point is 81 square, 281. Second point is 82 square, 282. What is the sum of the ordinates? You should know that abscissa means x coordinate and ordinate means y coordinate. So the sum of the ordinates here is 281 plus 282 for the first 2 points. Similarly, the sum of the ordinates here will be 283 plus 284. The question is saying that the sum of the ordinates here is equal to the sum of the ordinates here. So basically you're getting T1 plus T2 is equal to T3 plus T4 because T2A is common to both, right? Once we know this, we have to prove that the chord joining first 2 points is parallel to the chord joining second 2 points. And we discussed when we did the theory of the chords of a parabola, the slope of a chord is 2 by T1 plus T2. Remember, I told you that we need to remember this. Just remember the slope of the chord. The slope of any chord between two parametric points is 2 by T1 plus T2. And therefore, the chord here, the slope would be 2 by T3 plus T4. And obviously, the question itself has said that this is equal to this. So the slopes are same. So the lines are parallel, right? So that is pretty easy. Let's move on to the next problem. Okay. This question is important. Prove that the portion of the tangent intercepted between the point of contact and the directrix of the parabola y square is equal to 4ax subtends a right angle at the focus. So this is a super important property you should remember this property also. We will do the proof right now, but make a note of this property. There have been questions that have been asked in JEE based on this. So let's understand what is it saying. This is my parabola. This is my directrix. This is my focus. Let's say we have a tangent here like this to the parabola. The portion of the tangent intercepted between the point of contact, this is point P, let's say T, and the directrix. So this is x is equal to minus a. So this point Q. This portion PQ subtends 90 degree at the focus. That's the problem. That's what we need to prove. So this point is a comma 0. So we need to show that this angle is 90 degree. Okay. And this is an important property. It is very useful in certain types of questions. So make a note of this. We'll do the proof now. It is very simple to prove this. The tangent equation at point T would be Ty is equal to x plus at square. So point P is at square comma 2at. Now let's find point Q. Point Q will be where this tangent line meets the directrix, right? So if you put x is equal to minus a here, you should get the point Q's coordinates. You'll get Ty is equal to minus a plus at square. We get y is equal to a comma t square minus 1 by t. And x is equal to minus a. So Q is equal to minus a comma t square minus 1 by t. This is my point Q, right? Once I know point P and point Q, I already know S. So I'll find slope of PS. Slope of PS would be 2at minus 0 by at square minus a. So notice that a will get cancelled and it is 2t by t square minus 1. This is slope of PS, right? The slope of this line. What is the slope of QS? Slope of QS would be a t1 t square minus 1 by t minus 0. So a t square minus 1 by t on the numerator divided by minus a minus a. So minus 2a. So now we are getting here negative t square minus 1 by 2t, right? This is the slope of QS. Now you can see clearly slope of PS is 2t by t square minus 1 and slope of QS is minus of t square minus 1 by 2t. So obviously the product of the slopes is equal to minus 1. So the line PS and the line QS are perpendicular to each other. And therefore we have proved that the portion of the tangent intercepted between the point of contact and the directrix subtends a 90 degree at the focus, right? By the way, this also means that if you draw a circle with diameter PQ, then S lies on the focus. Think about it. If I draw a circle like this with diameter PQ, the circle will pass through the focus because this angle is 90 degree and this is my diameter and we get the angle in a semicircle is 90 degree from a chord property or a circle property that you might have learnt in lower classes. Angle in a semicircle is always 90 degree. That means S lies on the circle, right? So another way to say the same property is the circle drawn with PQ as a diameter will always pass through the focus, right? So very important property. Keep this in mind. Let's move to the next problem. Prove that the radius of the circle whose center is minus 4 comma 0 and which cuts the parabola y square is equal to 8x at A and B such that its common chord AB subtends a right angle at the vertex, subtends a right angle at the vertex of the parabola is equal to 4. So basically, we have a circle whose center is minus 4 comma 0 and which cuts the parabola, given parabola at A and B, such that the common chord AB subtends a right angle at the vertex of the parabola. Vertex of the parabola, by the way, will be 0, 0, right? Is equal to 4. We have to prove that the radius of the circle is equal to 4, right? So let's write the equation of the circle because center is given. We don't know the radius right now. So we'll say equation of the circle is x plus 4 whole square plus y square is equal to r square. This is my circle. And this cuts parabola y square is equal to 8x at points A, which is x1, y1, and B, which is x2, y2, right? So obviously, when a curve cuts another curve, we can try to solve the two equations together, and the points of intersection of these two are A and B, right? So if I put y square is equal to 8x in this, I will get x plus 4 whole square plus 8x is equal to r square. Why am I substituting 8x into this? Because I'm solving the two curves in order to find their intersection points. So this is an equation only in x. So the roots of this equation will be x1 and x2. And the roots will be real because they are cutting at two different points, right? So therefore, from here, if I simplify this quadratic a little bit, what I will get is x square. You will get a 8x here, so plus 16x, and you will get a 16 minus r square is equal to 0, right? So from this, I get that x1, x2, the product of the roots x1, x2 is equal to 16 minus r square, right? And obviously, we also know that y1 square is equal to 8x1 and y2 square is equal to 8x2. So the points would be the points y1 and y2 would be plus minus root 2 x1, right? So we can also solve for y1 and y2 from here. We will say that y1 would be plus minus root over 8x1 and y2 would be plus minus root over 8x2, right? So since the chord AB subtends a right angle at the vertex of the parabola, vertex of the parabola is 0, comma 0. So if you think about it, A and B could be 2 points. A is x1, y1 and B is x2, y2. And we know slope of this line would be y1 by x1 and slope of this line would be y2 by x2. And this has to subtend 90 degree. So we know that y1, y2 by x1, x2, a product of the slopes is minus 1. So y1, y2 should be minus x1, x2, right? That is the result that we know. Or x1, x2 plus y1, y2 should be equal to 0, right? This result we know. So now we already know x1, x2 is 16 minus r square plus y1, y2 is going to come out to be 8x1, x2. Because if you recall, y1 was root over 8x1 and y2 was root over 8x2. So when you multiply y1, y2, you will get 8x1, x2 is equal to 0. So basically, this is x1, x2 plus 8x1, x2. So we are getting x1, x2 is equal to 0. 9x1, x2 is 0. So x1, x2 is 0. But that means 16 minus r square is 0. And that means r square is 16. And basically r is equal to 4. There are other ways to do this problem also, but this definitely solves the problem. We have proved that that particular circle has a radius of 4. Okay. Let's move on to the next problem. In this problem, what we will look at is another important property that we will prove, but you should try and remember this property. Prove that the circle on a focal radius of a parabola as its diameter touches the tangent at the vertex. Touches the tangent at the vertex. So first of all, you have to understand what the question means. Basically, it is saying that we have a parabola. What is a focal radius? If there is a point here, and this is the focus S, and this is P, point T, and this is A comma 0. This line PS, the line PS is your focal radius. And what we need to do here is draw a circle with the focal radius as diameter. So something like this, a circle like this, with the focal radius as diameter. Obviously, this is not a very accurate figure because I'm trying to draw it by hand. We need to prove that the tangent at the vertex is also touching this circle. Okay. So first of all, I need the equation of this circle. So this point is at square comma 2at, and this point is a comma 0. So you know diametric form of a circle equation, we have to do x minus x1, x minus x2 plus y minus y1 into y minus y2 is equal to 0. That's the equation of diametric form of a circle if x1, y1 and x2, y2 are the end points of the diameter, right? So here our endpoints are at square comma 280 and a comma 0. So I'll get x minus a, x minus at square plus y minus 280 and y minus 0 is equal to 0. This is the equation of my circle. So if I simplify this a little bit, I'll get x square plus y square. There's a minus ax minus at square x coming here. So minus ax 1 plus t square here. And from here, I'm getting a minus 280y. And there is no constant left over here, but there is a constant a square t square left over here. Plus a square t square is equal to 0. This is my circle equation. In this circle, we can see that the center of the circle is obviously this point, midpoint, and you should realize that if this circle touches the tangent at the vertex, tangent at the vertex is x is equal to 0 line, right? X is equal to 0 line is the tangent at the vertex. So if x is equal to 0 line is a tangent to this, then what happens is you should be able to say that the perpendicular from the center to this must have perpendicular from center to this must be equal to the radius of the circle, right? So center's coordinates we can easily find. It is the midpoint of PS. So it is going to be a plus at square by 2 comma at. This is the coordinates of the center of the circle. Let's call it C. Now what is the length of the perpendicular from C to the y-axis? That is simply going to be its x coordinate, right? A plus at square by 2 is my length of the perpendicular. So I have to check whether a 1 plus t square by 2 is equal to the radius of the circle or not. This length should be radius of the circle. But radius of the circle can be figured out from the equation here. it is going to be root over g square plus f square minus c, right? So here it would be, g would be a 1 plus t square by 2 whole square plus f square would be a square t square minus c would be a square t square. So this cancels, and notice now that I am getting this as the radius because you are getting the same thing. A 1 plus t square by 2 is equal to a 1 plus t square by 2. So what I have proved is that this circle with the end points of a focal chord as the diameter has radius such that it is touching the y-axis, which was the tangent at the vertex. So remember this property that if you have a focal radius of a parabola, and if you draw a circle with the focal radius as the diameter, that circle will touch the tangent at the vertex. That is an important result to know. Let's move on to the next question. This says, prove that the orthocenter of the triangle formed by any three tangents to a parabola, any three tangents to the parabola lies on the directrix of the parabola. Okay. So first of all, how do we form a triangle with the tangent? So if the tangent is like this and another tangent is like this, and there is a third tangent which I'm not drawing right now, it will be awkward. Okay, we can draw it like this. Notice that these three tangents are intersecting at this point, and this point. So they have formed a triangle here. Let's call it A, B, C. And the points were T1, T2, T3. These were the points at which you drew the tangents, right? Now we have to prove that the orthocenter of ABC lies on the directrix of the parabola, right? So let's say the parabola equation is y square is equal to 4ax, and the points are a t1 square, 2at1, a t2 square, 2at2. These are the points on the parabola where tangents are being drawn. These are not the vertices of the triangle, right? So you know the point of intersection of two tangents. So for example, tangent at T1 and tangent at T2 will intersect at C, and the C coordinate is A T1 T2, A T1 plus T2. We have done this derivation in a previous video, right? So we know basically the coordinates of the triangle. They will be A T1 T2, A T1 plus T2. B would be A T2 T3, A T2 plus T3. And C would be A T3 T1, A T3 plus T1. These are the three coordinates of my triangle, and I have to find the orthocenter of this triangle. So orthocenter of this triangle is going to come by thinking of the lines which are from a particular vertex and perpendicular to the opposite side, right? So let's think about the tangent at the point T3. The equation of this tangent was what? Equation of tangent is T3y is equal to x plus a T3 square, right? So what is the slope of this tangent? Slope of this tangent is 1 by T3. So the line perpendicular to the tangent should have slope of minus T3, right? And the line perpendicular to the tangent and passing through C is the altitude, right? So equation of this line should be passing through C. So it should be y minus a T3 plus T1 actually my labeling is slightly wrong. This point is the intersection of tangents from here and here. So C is not actually this. C is going to be A T1 T2 A T1 plus T2. So this one would be A T1 plus T2 is equal to, the slope of my required line is minus T3 and x minus A T1 T2. This is my altitude and I need to find another altitude like this. If you simplify this equation becomes T3x plus y, T3x plus y minus AT1 minus AT2 and plus AT1 T2 T3. Okay, so I'll write it as AT1 T2 T3 plus AT1 plus AT2. This is the equation of one altitude. I need another altitude equation. You have to repeat the same process, and what you will get, the other altitude equation would be something like this. T1x plus y is equal to A T1 T2 T3 plus A T2 plus A T3. This will be a second altitude. And now I have to get the point of intersection of these two. So in order to do that, we subtract the equations and we get T1 minus T3x is equal to, this term gets cancelled, A T2 gets cancelled, and you are getting A T3 minus T1. And clearly from here, you can see x is equal to minus A is the point of intersection. So if x is equal to minus A is the point of intersection, that means that is our orthocenter, and therefore you can easily see that it lies on the directrix of the parabola. So again, the question is easy if slightly long. However, there are a couple of things here you need to remember. What is the point of intersection of tangents to a parabola? That result is super important, has to be remembered. And also, if you form a triangle using any three tangents to the parabola, just remember the result that the orthocenter's x coordinate will be on the directrix of the parabola, right? So more or less the standard theory of parabola is over. I will do one more class for theory, which will basically cover some of the more advanced properties. And after that, it will be about problem solving, right? So expect one more video covering some of the more advanced properties of a parabola. I will do that in the coming days. And after that, we'll go on to problems and ellipse and hyperbola and so on. So that's it for this video. I hope you're learning from the series. Please like the videos, subscribe to the channel, and share it with your friends. And I'll see you next time.